the last lecture, we discussed the units in measurements. Today, we'll continue to talk about the numbers in a measurement. We have all used numbers almost every day in our life. However, the numbers we encounter in our life actually can be divided into two different categories. The first one is called exact number. Those are the numbers that have no uncertainty in them. When you say those numbers, you know those numbers are exactly correct. For example, when you say a dozen, you know you mean 12. The definitions, okay? 1 meter equals 100 centimeter. Guaranteed, it must be 100 centimeter. No more, no less. Counting, I have 12 marbles. That 12 is exact. I have 3 siblings. There are 4 people in my family. Those are exact numbers. There are no uncertainty in those numbers. And some simple fractions. Another kind of numbers, however, they are always associated with some kind of uncertainty in them. They are called inexact numbers. Anytime when a measurement is taken, the data reported will always have uncertainties. Okay, we just clarified that. Anytime a measurement is taken, the number, the data reported will be an inexact number. It will have some uncertainty in it. But what is uncertainty? Let's first clarify that. Uncertainty is a digit in a number that must be estimated. That number, that digit, we'll call is uncertain digit. All measurement will have some uncertainty in them. How? Why? What are we talking about? If all measurements will have some uncertainty, now next time when you ask me to do a measurement in the lab, can I just make up a data and tell you that, okay, I estimated? Well, you cannot do that because the estimate you make about a measurement must be reasonable, must be acceptable. Now it comes down to another question. What kind of uncertainty or estimate is reasonable, is acceptable? Well, before I go into the details of that, let's use a real life example to talk about that first. Assume someone is asking me about my body weight. Say, hey, George, what is your body weight? I will say, my body weight is 176 pounds. Now, if you look at me, if you can see me, you look at me and say, oh yeah, more or less, that's about to be right. Well, when someone asks me about a body weight, I hesitated. I will hesitate a little bit. Okay, like I said, 176. The reason I hesitate is because, number one, I know my body weight fluctuates along the days or even different times of a day. Number one. Number two, I want to give you my best estimate. What is the best estimate? When I say 176, the number 1 and 7, I don't need to hesitate to say that. I hesitated a little bit is because I was thinking about the last digit, number 6. I finally decided to say 176 is because I believe, at least I believe my body weight is 176 other than 177 or 175. In other words, in my not with all my best knowledge, I will say 6 is the closest number I think it should be. Well, it's an estimate. Okay, that number 6 is an estimate. Let's think about a different scenario or scenarios. If someone asks me, "Hey George, what is your body weight?" And I'll say, "Oh, my body weight is 198 pounds." Or I say, "My body weight is 175.80441 pounds." Now, if you guys can see me and you ask me about my body weight and I gave you either of the two numbers, you're going to think, "Oh, wait a minute. I don't want to learn chemistry with this guy. It doesn't make any sense." What's wrong? Why when you look at me, you can accept this number, but you will feel like if I answer your question, my body weight question with these two numbers, you will think this is ridiculous, doesn't make any sense. Why? Because when you look at me, you know there's no way I can have 190 something. That 9 has uncertainty. Or when you look at this number, you know, okay, that number can change any time. The any number after that doesn't make any sense. Combine all these three numbers, three answers I may give you, we can have some idea about the allowable uncertainty in a measurement. In a good measurement, in the right measurement, you always record all the certain digits, in this case 1 and 7, you know they're certain, you know they're right, and only one, the first one, uncertain digit, 6 in this case. Once you encountered the estimate, the uncertain digit, you stop, you do not continue. Okay, this one, when it encountered the first uncertain digit, it kept going. Doesn't make any sense. This one, there are too many uncertainties. There are two uncertainties. That digit is uncertain already. That number, there's no reason for you to continue. So a good measurement always includes all the certain digits plus one, only one uncertain digit. Wow, how do I know which digit is uncertain then? You give me a tool, you give me a ruler, okay, and ask me to measure the length of something. How do I know to which digit I will report? How do I know which digit will be the estimate? Well, with any measuring tool, used, you always report all the digits that the tool tells you that it has marks on, and only one digit that you cannot tell based on a mark. So you always go to one digit after the finest marks, the smallest scales on the measuring tool. If this statement sounds a little confusing to you, let's move on to the next slide. We may have a better idea about this. Okay, again, you always report all the numbers you can see from the measuring tool and then estimate one digit. Let's look at the example. in the measuring of the length of a sample. Hopefully this can help us to understand the last statement better. Remember, the last statement says that when you take a measurement, you always go to one digit after the smallest marks on the tool. So let's look at this. The first scenario, we're using ruler A to measure the length of this sample. Ruler A is marked by 1 centimeter. Ruler A is marked by 1 centimeter, or we can say it's marked by ones. Each mark is 1 centimeter. Now, you go to the length, read the length of this sample. 1, 2, 3. Okay, guaranteed is 3 point something. 3, correct. No uncertainty. However, 3 point what? Now you have to estimate. You look based on the position of the end of the sample, you estimate 3.7. Here, everyone's eyes may be a little bit different. You may estimate 0.6 or 0.8. Those are all reasonable. However, you do not want to estimate 3.5. Clearly, that length, the end point, is not in the middle of 3 and 4. So 7 is an estimate. Once you make an estimate, you stop. You do not keep reporting. Only one estimate. As we can see, with this ruler, our reported data will be 1 digit after the marks. The mark is on the 1st digit. We go to the 10th digit. Now let's switch this to this ruler. Okay, this ruler, every single small, there's count the small marks here. Every single small mark is 0.1 centimeter. We say this ruler is marked by 10th, 1 digit after decimal. It is marked by 0.1 basically. So now you look at the location of the sample. It is 3 point guarantee, 3 passed, 0.5, 0.6, 0.7. It is on the right of 0.7, 3.7 something. 3, 7, all correct. No uncertainty. You can read them from the ruler. Now 3.7 what? You have to estimate. There is no marks anymore. Okay, the author estimated is 0.4. It is a little bit to the left between 0.7 and 0.8. Okay, 0.4. Now the 4 is an estimate. Now the same sample with 2 different rulers, you come up with 2 different kinds of measurement data. Which one is correct? Both are correct. With this ruler, you must report 3.7. You cannot report 3.74. If you do that, it is incorrect. With this ruler, you must report 3.74. You cannot report 3.7. Hopefully, this explains that a measurement is dependent on the tool you're using. The correct data, the correct result always go to 1 digit after the smallest marks on the tool. Clearly, measurement obtained with ruler A will have greater uncertainty than ruler B. We say ruler B is more precise than ruler A. Now we do see examples telling us that when you report a measurement, you always report all the certain digits and only one uncertain digit. You do not report anything after the estimated digits. Any digit after that, they do not make sense. All the certain digit plus one, only one estimate are numbers that make sense, that are reasonable, we call those numbers in the measurement all the certain digit and one uncertain digit. We call them significant figures. They are the numbers that are significant for the measurement. Significant figures are all the certain digits plus one, only one estimated digit. Let's make it clear. Significant figures is only a concept for measurement. Only when you talk about the measurement, you have a significant figure issue. Now, given a measurement tool, we know how to take the measurement to which digit we will report. However, that is still not enough for us to present our data on the paper. There are some rules in the format of reported measurement data. We need to learn those rules before we can report our correctly measured data correctly. So we're going to go through some guidelines for determining sig figs. Number one, all non-zero digits in the measurement are significant. If a reported data is 3, 4, 5, 6, that number, that measurement has 4 sig figs. It has 4 sig figs. It means that the number 3, 4, 5 in the data are certain. The number 6, the last digit, is an estimate. The person, whoever took the measurement, believed the measurement is closer to 3,456 other than 3,457 or 3,455. The 6 is an estimate. What about non-zeros in the measurement? Well, there are 3 different kinds of non-zero digits. Leading zeros. Leading zeros are zeros at the beginning of a number. Again, we're talking about a measurement. They are not significant. If a measured data on the report is 0.048, that one only has 2 sig figs. Leading zeros are not significant. What does that mean by saying 2 sig figs? 2 sig figs means that the person who took the measurement believes the measurement is closer to 0.048 other than 0.049 or 0.047. The 4 is certain, no problem, guaranteed correct. The 8 is an estimate. That's what it means. So leading zeros are not significant. Confined zeros, zeros between non-zero digits, they are significant. A reported data measurement 16.07 has 4 sig figs. Again, what does this number mean? This number means that the number is closer to 16.07 other than 16.08 or 16.06. The 16.0, these are certain digits. 7 is an estimate. The last number is an estimate. Trailing zeros. Trailing zeros are zeros at the end of a number. They are significant only if the number has a decimal, which means if the number doesn't have a decimal, trailing zeros are not significant. Oh, 9.300, it has 4 sig figs. This number tells you the measurement is closer to 9.300 other than 9.301 or 9.299. The last zero is uncertain, is an estimate. Well, I measured data is 150. There's a trillion zero. There's no decimal in this number. So there are only two sig figs. 1 and 5 are significant figures. What does that mean? That means the 5, the last digit of the sig fig, is an estimate. That means this number, this measurement, is closer to 150 other than 160 or 140. Okay, the 5 is an estimate. In other words, the error of this measurement comes by tens. Every time you make a mistake, it makes an error of 10. The error in this measurement will be 0.001. Make sense? Practice. How many sig figs are there in each of the following measurement? Leading zeros, not significant. Confined zero, significant. Trillion zero, there's a decimal, it is significant. So this one has 4 sig figs. The last zero at the end is the estimate. 210, there's no decimal. There's a trillion zero. Trillion zero, if there's no decimal, is not significant. So there are only 2 sig figs. The 1 is an estimate. Whoever took this measurement, that person believed the data, the measurement is closer to 210 other than 220 or 200. 12,000, a number with no decimal, 3 trillion zeros. They are not significant, so there are only 2 sig figs. There are only 2 sig figs. What does that mean? That means the number 2 in this report, in this data, is an estimate. It's uncertain. That means the person took the measurement, believed the measurement is closer to 12,000 other than 13,000 or 11,000. The error of this measurement comes by 1,000. Make sense? Let's come back to the second one, the second practice. Measurement that comes up as 210. You took, for example, you took a measurement. This is what you report. You look at your number, you report it as 210 as it is like this. And we all know that this number, this measurement means that the actual number is 210, is closer to 210 other than 220 or 200. Wait a minute. What if this is what I want to report? What if I took a measurement and the value of our measurement is 210 other than 211 or 209? What if I want a number, a measurement that is 210 other than 211 or 209? How do I report it? Oh, I just write it 210. You cannot do that because we just understand that if you report 210, that is the meaning of 210 in the measurement. It is not this meaning here. I hope you guys understand what I'm trying to say. If you report a measurement as 210, you're telling other people your measurement is 210 other than 200 or 220. What if that's not what you want to do? What if your measurement you believe is 210? In other words, the uncertainty comes from the last digit. How to report? Okay, this is how you report. You will simply add a point decimal to the end of the number. The decimal will make the ending zero significant. So 210 point in the measurement means your measurement is closer to 210 other than 211 or 209. I hope that makes sense to you. Now we see that a measurement reported data, if someone reported 210, another one reported 210 with a decimal, these two measurements have a big difference. The first reported data, the error comes by tens. The second reported data, the error comes by ones. Let's clarify before I let you guys go. Okay. You only add a decimal to the end of a number when you want to make the trailing zeros significant. You would not randomly add a decimal to any number. Okay. You only add a decimal to the end of a number when you want to make the trailing zeros significant. See you next time.